So I will share this presentation. I mean, it has been prepared with Francesco Vanzini, who is here, and will give the 4th lecture. And I will simply do the intro with slides, and then I will move to the blackboard. But to give you a little perspective, I think it's going to be quite different from the lecture you had until now, because I come more from theoretical physics. So we will really start with thermodynamics, try with the basic principle of thermodynamics to build up the energetics of chemical reaction networks. And then when we will go to the 3rd lecture, I will make connection to biology. So to simply kind of give you a small historical perspective, okay, in the 19th century, towards the end, there were pioneers in equilibrium thermodynamics in the context of chemistry. Gibbs not only in the context of chemistry, but he did important contribution to physical chemistry. And then in the 1920s onwards, what is sometimes called the Brussels School, which started with de Donder, who is an important figure, not so known, but a close correspondent to Einstein. And he was in Brussels, and I was trained in Brussels, so I got corrupted there. So he founded this school, and they started developing irreversible thermodynamics. A student of de Donder was Prigogine, who got the Nobel Prize in '77 for the discovery of dissipative structure, or explaining how, when one goes away from equilibrium, new phenomena can emerge that are not existing at equilibrium, like patterns, oscillation, chaotic behaviors. And Nicolis, who was my teacher of statistical physics, was a student of Prigogine, and my PhD advisor was a student of a PhD student of Nicolis. So this is the line where I come from. Van Rysselberghe was a student of de Donder. He's also not very well known, but I realized recently, digging in the old literature, that is actually a quite important figure, because when we will talk about local detail balance, remember his name. He was one of the person really putting emphasis on this, and this connection between thermodynamics and kinetics that is really central for what I'm going to present. And then there's the mathematics community. This is actually interesting, that one of the famous names is Feinberg, but there are many others who studied dynamics of chemical reaction networks as mathematician, interested in proving how, if there is a Lyapunov function, so if the system relaxes to a unique steady state and things like that, in connection to the key quantity that is a stoichiometric matrix, which encodes the topology of the network. We will speak about all these things. And this is really where topology enters the field. And this will play a key role in what I'm going to present in the 2nd lecture. Then Hill is a pioneer too, less formally than the mathematician, but he understood the importance of cycles and applied it to understand energy transduction in the context of biology, mostly molecular motors, not full chemical reaction networks, because it's only true for unimolecular chemical reaction networks. And then some people started putting the stoichiometric matrix in the works of this school, but without really fully using the topological property of this stoichiometric matrix. And what I'm going to do is really put together this tradition of non-equilibrium thermodynamics of chemical reactions. They were not really talking of networks. They were really focused on a few reactions, combining with these topological studies of the mathematicians, and show you that actually, I think this is probably the most important thing that we understood, is that if you want to know what are the thermodynamic forces and the thermodynamic potential describing a chemical reaction networks out of equilibrium, you really need the topology. The forces are going to be dictated by the topology. So the first lecture will be actually almost in the same vein as what was done at this level, really dynamics and thermodynamics, introducing the stoichiometric matrix, but not really fully making use of it. In the second one, we will really use topology and identify these forces and potential. Then, well, let me first go directly to that. In the third, we will apply this to energy conversion. And I will show you how to develop the formalism using circuit theory to study more complex chemical reaction network. And the first lecture by Francesco will be how information naturally emerges from these non-equilibrium thermodynamic descriptions. And just to comment here, the previous slide was really thermodynamic based, but now kind of a bit more biologically speaking. What I was saying before, that realizing that at equilibrium, all these phenomena like oscillations, petal formation, active matter, this collective behavior that we got a lecture last week on active matter, kinetic proofreading, this was also discussed. So many things by now were discussed: molecular motors, information processing, and metabolism. This is really the non-equilibrium chemistry powering biological systems. So my approach is like, okay, if we want to understand biology in a kind of fundamental sense, more physicsy way, it's very important to have a clear understanding of the energetics and dynamics of chemical reaction network when they are driven out of equilibrium. So that's really going to be the key point. And actually, all these things we applied our formalisms to. I will, of course, not have time to cover them. I will mostly focus on metabolism and Francesco on information processing. But at the very end, I will give you a slide where you can find references if you want to go, for instance, on pattern formations, active matter, it's ongoing, and things like that. Okay, so that's the kind of the plan. Yes, this is Francesco wanted me to present that because it was on his slide. But I think it's a nice idea to present kind of as a teaser the importance of how chemical reactions can be non-trivial in terms of generating thermodynamic forces. So imagine that you have a system with a species A in contact with a bath at temperature T and a chemostat at a given chemical potential. A chemostat, so it's something that can exchange the species E, it can go in and out from the system. This species will be at equilibrium at this chemical potential and at that temperature. This is all intuitive. Huh? I'm trying to give you a feeling. If you now put two temperature, you kind of expect, from intuition that you're going to have a heat flow from the hot to the cold reservoir. And similarly, if you have two chemostats at different chemical potential, you will have a flow of A from the higher chemical potential to the lower chemical potential. Okay, this is kind of obvious from our intuition. Now let's put two species with one chemostat of A and one of B, but there's no way to convert A into B. So that system is at equilibrium because there's no flux going from one chemostat to another. Here, we had fluxes, so the system was out of equilibrium. We say that we break detail balance when there are fluxes. So here there are none because A and B cannot be interconverted. But when we turn on the reaction between A and B, now the flux can appear, right? Because this goes to A goes to B, and then B goes to this guy. But look, now I put a slightly more complicated reaction. A gives B plus C, and I tell you that this system will actually not go out of equilibrium, it will reach equilibrium. And that's kind of, maybe you can kind of guess, but it's not so easy already for one reaction. Okay, because what will happen is that C will accumulate in such a way to equilibrate this reaction. But that's one reaction. So when you have a chemical reaction network, understanding when you will have or will not have a non-equilibrium state, which will generate currents, is not so trivial. So that's kind of to give you a flavor of why topology is important. Okay, and now let's start.
Sorry, could I ask a quick question?
Yeah.
So, sorry, what was meant by the second one?
By the second one?
Yeah, what's happening in the second one?
This one, huh?
It's just A, and something is being transferred from one place to another, and temperature.
Yeah, so if you have a temperature gradient, there's going to be a flow of energy from the hot to the cold reservoir across the system. And if there's a chemical potential of A higher than the chemical potential of A in this chemostat, there will be this chemostat will deliver A's to the system, and these A's will then move to the chemostat at lower chemical potential.
So are we imagining like two beakers connected?
Yeah, imagine simply that the concentration here is much higher than here. These are very large systems with lots of A, so that the flux is basically not modifying their total amount. And you're looking at this evolution where, because the concentration is much higher here, slowly particle will move out from this one to this one. Okay?
I had a question. So in the second last and the last
this one?
Diagrams, yeah. Can you give some intuition as to why in one case you would expect broken detail balance and in the other case you would have detail balance?
So, I mean, this is the teaser. So this is what I want Francesco to explain once I will present the formalism, how you can really see it cleanly. But the intuition is that C will accumulate to a value that will basically cancel the net flux in this reaction. And that's why you will reach an equilibrium. But the real rigorous explanation will come. Okay, and this is when I start my Blackboard presentation. Yeah, I think I will anyway draw all this on the Blackboard. So let me take my notes now. And because the starting point is important, I really want everybody to understand. Okay, so I'm going to draw this chemical reaction network to explain you all the quantities that appear in, well, let me first put a title. So this is part 1. And I start with A, which is dynamics. So we will dynamics of chemical reaction networks, and I will start with closed. Do I write big enough for the people in the, a bit bigger? Okay. CRN stands for chemical reaction network, okay? The S, chemical reaction networks. So what do I mean by chemical reaction networks? It's what we had. This is the example I will use throughout my lecture. And then with Francesco, you will see different examples. So let's have these different species here. Like this. And now I give, by convention, a direction to every reaction, okay? It's a convention. So here I have S going in. Here I have P going out. So here the direction is like this. This reaction I will call reaction 4. This one is reaction 5. Now I have a reaction 2 that converts this into this. A reaction 3 that spits out the W, and a reaction 1 that takes in F. Okay? So that's going to be the model. I will keep it there for the rest. And we are thinking of this as a closed box in the sense that there's no species at the moment going in and out. And I will always consider constant temperature, constant pressure. Okay. Pressure effects will not be relevant because in any case, we always think that we are working in a solution in water, if you want to think of biology, and that we are diluted. Okay, so water constitutes most of the volume, and so pressure effects will be irrelevant. And temperature, I mean, it would be interesting to generalize to non-isothermal, but all the things I will present are isothermal. Okay, now dynamics is described by this. I have a vector of concentration, and we will go through all of these quantities. The key quantity that I mentioned before, the stoichiometric matrix, and the current of every reaction. Okay, so let's start with Z. So Z is a vector that contains all of the species that I've drawn in my chemical reaction network. Okay, so E, EF, EW, EFS, EW. I rank them in the right way because of what I'm going to do later. That's why. Here we go. That's the vector Z. Okay. And these are all concentrations. I'm not sure I'm going to always write the little bracket for concentration. Maybe to speed up at some point, I will drop it. Now we have the vector of reactions. So here, how many reactions do we have? We have 5. Okay, so and every flux will depend on the concentrations. So we have J1, J2, J3, J4, J5. This. And now comes the stoichiometric matrix. So the stoichiometric matrix, usually one splits it into the stoichiometric coefficients of the products minus the stoichiometric coefficients of the reactant. So, and each of them are positive. So you will see when I fill now S, every negative number will be associated to this mu plus. Every positive number will be associated to mu minus. So reactant products. And now let's fill this stoichiometric matrix. This is really important, so that's why I really want to do it on the blackboard step by step. Maybe at least for the first lines. So this stoichiometric matrix connects the fluxes to the species. Okay. So what we should imagine is here the vector of fluxes, and I'm acting on it. So what I'm having here is the different. I can space it a bit more. 2, 3, 4, 5. The reactions, and here I have the species. E, EF, EW, EFS, EW, S, F. Okay, and now, I mean, depending on what prefers, one can either pick a species and look at how every reaction produces or consumes it, or one can take a reaction and see this reaction, what it consumes and what it produces in terms of species. So let's take reaction 1. So reaction 1 is this one. I'm consuming E, 1E and 1F. So that's going to be 1E minus 1, 1F minus 1. and I am producing a EF. So this is going to be a 1, and all the other terms will be 0. Here? This is really important. Huh? So let's move to reaction 2. I'm consuming EF, I'm producing EW. So consuming EF means -1, producing EW, 1, and all the other species are not involved, so 0. Okay, let's do 3, and then I will fill the rest quickly. 3 consumes EW and produces E and W. So consumes EW and produces E and W. Okay. Now I fill quickly the other ones. 0, -1, 0, 1, 0, 0, -1, 0, and the last one is 0, 0, 1, -1, 1, 0, 0, 0. Good. So, yeah, this is S. Huh? The stoichiometric matrix, it's called. Now, what about the form of the fluxes? Because this is a purely, when I speak of topology of the chemical reaction network, I mean this object. Because this guy, it's only telling me how reactions are connected, are acting on species. Okay, it has no information about the dynamics. The dynamics is all encoded in the flux. And for simplicity, I will consider ideal solution. We've generalized the theory to also non-ideal solution within mean field, as usually treated in chemistry when there are non-idealities. But this makes the formalism significantly heavier and not so conceptually, it doesn't change it so much conceptually. So this is why I will focus always on ideal solution. And in ideal solution, we have what is called mass action law. And mass action law tells us that the flux across a reaction rho is always written as the difference between, well, actually this is not mass action, this is general. The flux across a reaction can be always split in the reaction, the flux in one direction versus the flux in the other direction. So minus rho means the sign, the direction of the reaction opposite to my convention. And mass action law tells us that these is the form of these R rho is K rho, the kinetic constant, times the concentration to the power of the stoichiometric coefficient. Now, the notation might be a bit surprising to you. It's a compact notation. I need to explain it. So this is minus rho. And this is minus rho. Because you see, I have a vector to the power of a vector. You should read this component-wise. So this means when I write z s or z nu like this, you should read this as a product over the species z alpha nu alpha, alpha rho. Okay, so it's a product of all the z's to the power of the stoichiometric coefficient. So when we look at the flux in the direction of rho, what we are saying here is that there's a kinetic constant, which is This, in principle, if you want to know it, it's a quantum mechanical problem. But usually these are things that we can measure and characterize.
Sorry, could you just explain that again with the product-wise, so the component-wise exponent?
So you should take this as a definition. Okay. So what I'm saying here is that you simply need to take it component-wise as a product. So the definition of this is that it's a product of the concentrations to the power. I will give examples now. So yeah, so the flux in this direction is proportional to the concentration of the reactant. That's why it's to the power of the exponents of the reactant. So let's take a first example. Reaction 1. Is going to be K1, and now this is the kinetic constant, multiplying F times E. So I'm saying that the flux here is proportional to the concentration of these two species, and they have stoichiometric coefficient 1, so it's going to be, what did I say? F times E. And R minus 1 is going to be K minus 1 times. Now, this is the product. So this flux is proportional to how many EF we have. And this is very intuitive. You can think of it as a probabilistic argument. The more there are molecules, the more likely it is that they're going to collide. And this is essentially what you get. Okay?
So here in all the cases, all these reactions are reversible.
Yes. Mass action law. In reality, reactions must be reversible from the reversibility of physics. When you see a reversible reaction, it simply means that one of these flux is much higher than the other one. Think of it like that. But microscopically, there are always processes going backwards. Good. What else did I want to say here? I think by now, I think you understand the meaning of this. Can I assume this safely? Yes, yeah. So these vectors, you see, so think of, so let me say this. So all the ones, let's take a row here. All the ones, so here actually there's only one, is mu minus. All the minuses are mu plus. So this one and this one is mu minus. And the rest of the elements of these guys are 0. It's arbitrary at the beginning, but once you choose this, you need to stick with your convention, right? So choose it at the beginning and then stick to it. So that's why I put arrows here to give my sign convention. It doesn't mean that the reactions are irreversible. They happen in both directions. Simply, the arrow I put is to define the convention I want. Yes?
Is there any specification with respect to the order of the reactions? As in 0 order, first order, second order?
Yeah, it's true that I picked all, in the example I have, you will give examples with stoichiometry too? No. Well, we can give you an example, but if you would have, I don't know, 2F here, then in the mass action, the F would go to the power 2.
Yeah.
So it's true that we have only ones and zeros and minus ones. If you have B molecular reactions, you would get 2s and minus 2s.
Right. So that will be the stoichiometry. But apart from that, if it's dependent on only one reactant, it's first order, or if it's not dependent on the reactants at all, 0 order. So that in that way, what would be the order that we are following here? Second order or first order? I'm getting a bit confused.
So what do you mean by order?
So in chemical kinetics, we follow that which order of reactions we are.
But okay, I assume that the reactions are always elementary.
Okay.
So these are always, at this moment, I will tell you later that I don't need this assumption. This is going to be in part 3. But for the moment, I assume elementary reactions, which I think in terms of order means that it's the order would be how many, this is far right, it's how many concentrations I have here. So this would be order 2, this would be order 1.
I see.
But it's think of them as elementary reaction. Okay? We assume that we know all elementary mechanisms. And I will then give you a theory to how you can coarse grain and go to effective reactions, and there your question can be rediscussed. Yes?
So, Nicholas mentioned that reactions are not included there for mass action.
Not at the moment, yes.
And you say that that is a non-ideal solution, or what?
No, I said it is ideal.
Yes.
But so I'm doing the simplest case for pedagogical purpose. I can generalize to non-ideal, but I don't want to do it because this complicates things. But it can be done, and we have a paper on that. This I will not speak about, but we can also do non-elementary reactions, and that will be really the topic of the third lecture. So at the end, we will be able to treat enzymatic reactions, but I want to build from the elementary level.
So you, but Nicholas mentioned in your language is non-ideal. Is that right?
It's not elementary.
It's not elementary.
Yeah, let's distinguish. Okay, ideality refers to the fact that molecules are interacting. Okay, so when I say ideal solution, it means that the molecules are not interacting. It's like an ideal gas, but it's the analog of the ideal gas in the solution. When I'm saying elementary, it means that the reactions I'm writing, you can really think of them as collision events at the molecular level. Michaelis-Menten I would have intermediate steps, right? And this is why it's not an elementary reaction. You have a mechanism. Here, the only mechanism is the collision.
So this system is not an ideal solution. Is this an ideal solution that you're talking about here?
I'm talking always, let's put it clearly, ideal and elementary reaction.
So in what sense is it ideal?
That the species do not interact. So E and F do not interact. Their energy is only the energy contained in the molecule. So the energy of E is the energy of what is contained in the molecule of E, the one of F in the molecule of F, and there's no contribution due to the fact that they would bind or, repel, whatever.
Although EF, the formation of EF is actually a binding event, right?
Yeah, but it's a collision.
Mm-hmm.
So this is very different to have interactions that are not of a reactive type, two charged two charged molecules, and the collision event that generates a covalent bond.
Okay.
So I'm still a little confused about the reversibility of these edges. So like in this.
About the what?
About the reversibility of these edges, because like we're not accounting for that in this S matrix, right?
No, the stoichiometric matrix acts on the flux, but the flux is a flux that contains, here. It's the flux that contains the flux from the forward minus the flux from the backward. So this guy really takes into account the net. This whole thing is the net. This is the flux in one direction minus the flux in the other. So if you want, R1 was this one. So we had F plus E going to EF with the sign convention that it goes this way. Okay? So this is the rate with which this reaction happens this way. This is the rate in which it happens this way. Okay?
was just a little confused. Got it.
Good. I move on now. Otherwise, I will not finish. Now let's open the system. Very important. Let's do here. Open CRN. And since Francesco likes color, I'm going to use color. So what does it mean I open the system? It means that I now allow for exchange processes with the outside world. Okay, so what Francesco likes to draw is a beaker like this of F, and then a beaker of W, etc. So you imagine here that you have a large amount of S, or a source of S, that can provide from the outside PW, SPWF. How does this change our dynamics? And you see, this is why I ordered my matrix in the following way, because I want to distinguish now those pieces that are exchanged. And as you can see, I chose it just the right way, because these are the internal species, these are the external species. And same thing for my stoichiometric matrix. I can now split it into the part that acts on the internal species and the part acting on the exchange species. So this part we will call SX, and this part we will call XY, because these species here, this vector here we will call X, and this vector here we will call Y.
Excuse me, I just have a question. When you, for your first equation, so S times G, S is a stoichiometric matrix and G is a vector.
Yes.
But so I was just wondering, what is the mathematical production of this product? Like, I don't know, you multiply a matrix per. Just
so
what
if
is
you
the
want component-wise, this is rho reactions. This is a matrix that has species and reaction, and this has species. And so here there is a sum over rho.
But how do you make the calculation between the matrix and the vector?
This is a regular matrix product. So the way you fill it is you do.
But in which extent G is a matrix? Because here it seems that this is a vector.
No, J is a vector. This is a vector, this is a matrix.
Okay.
That's why I use 2 bar for my matrices, 1 bar for vectors. Yes, so I define Sx. Yes, so what I can do now is basically I can split if you want. Let's first write the one for dz, still at the full level. It's like stoichiometric matrix acting on J plus now the current of the exchange species. But I can resolve this more by splitting the z as I did in dx dt is the x part of the matrix acting on G. And there I don't have an exchange flux because these are the internal species. And the exchange species, they now are defined like this. Okay? And so in other words, what I'm saying is that the vector I, you can, to emphasize this, it's implicit in what I wrote, is that the vector I is made of a IY part and a 0 part in X. Because I'm not exchanging X, I'm only exchanging Y. Yes.
The concentration of the external reservoir doesn't matter.
Wait. It matters. Wait, let me get there. So now I only defined the flux, which is, by the way, a vector. This is also a vector. So now, precisely, okay, good. I have a balance equation. X are only consumed by reactions, but Y are consumed by reactions and exchange. So now actually comes the question of the different ways of controlling a system. And we kind of introduced this terminology. So the simplest and most common one is what we call concentration control. So what the way you think of it here is that this is the object that is controlled. Okay, so in other words, and very often, what it means is that you fix its concentration, and it's going to be assumed constant. But it doesn't need to. But that's really the most common way of generating a chemostat. Is you say, okay, Y here, whenever Y gets consumed by reaction 1, I imagine that there's a huge supply of F that blick brings it back. Okay, and whenever it's produced, it's eliminated. So that the concentration of F is going to be constant. This is often in practice achieved by simply putting a large quantity of F, so that over the scales that you care about, you can assume that it's constant. Okay, so that's the most common one. And very often it's assumed even constant. I leave it like that because it could be time dependent, but very often it's assumed to be constant. Yeah. Yes, this is really the vector. So let's write it. Y is in the order, it's IP, IW, IS, IF. So and this is really the flux. So number of molecule per unit time, or mole, that you provide here. So this flux. Zero X bar. It's simply that it's all zeros. So it's 0, 0, 0, 0, 0. How many do I have? 4. Okay. Because those species are not exchanged. You see those ones. No, sorry. I'm not dividing vectors. Okay, concentration control is one of them. Now the second one could be flux control. And in flux control, what you control is the flux. Okay, so you are supplying at a rate that you measure, and then reactions are consuming, and the species abundances can change. And there are, of course, also more complicated mix control, if you want, that are interpolations between these type of controls. And I only mention because some species can be flux controlled, other can be concentration controlled. But a common thing is the so-called CSTR, continuous tiered tank reactor, which is it's something like this. You basically supply a certain amount of species with a given rate. So that would be flux control, but only a few of them. And then you eliminate, it's well mixed. That's why it's continuously stirred. And you eliminate everything at a constant rate, okay? So in that case, those species that you supply will contain a fixed I, but all species will have an elimination rate that is proportional to their concentration. That's one example of continuous stir tank reactor. Okay. I'm supplying, let's say, these two species, F and W, at a constant rate. Then I'm mixing here, and the reactions go on. And I'm eliminating here with a tube everything. You see? So all of these species will be eliminated at a rate that is proportional to their concentration.
So what does CSTR mean? How?
Continuously stirred tank reactor. This is used in engineering, and more also chemists are now interested precisely to do synthesis out of equilibrium. And so it's been, I think there's again more and more interest in basic chemistry for these kind of reactors.
So I'm a bit confused about what is meant by the flux control. Like if we are controlling the inputs, like the substrates, and I was assuming flux to be one of the outputs which we will sort of gauge from how it changes. But if we are putting a control on the flux and mixed control, so basically I'm not getting the idea as to what are the controls.
So I mean, it's because it really depends on the experimental setup that you're looking at. So this is basically, here I'm modeling these different ways of controls. How to actually implement it in the lab is a different issue. I mean, this is a commonly implemented system in the lab. Concentration control also by simply putting large abundances. Here you would need to find a way to supply at a constant rate. And I think, in the CSTR, you are supplying certain species at a constant rate. So with a tube of pure chemicals that enter and then get mixed.
What is the flux exactly that we are controlling there? The turnover, is it? Substrate to product, or what flux?
No, it's the entrance flux. So it's really this guy. So these are, this is IF, this is IW. So it's these fluxes here.
Right, entry and exit fluxes.
Yeah, by convention, they are all entries. But if they are negative, then they are exit.
See, so I was thinking the ones that are leaving the system, like P is leaving the system. So that is also supplied, or that is supposed to go out of the system?
Depending on your control mechanism, you may have a positive or a negative one. They can be both. Again, this is a sign convention.
Right. Good.
Then how you implement it in practice depends on the setup. But I think this covers everything. Yes. Yes.
Then even the first 4 elements of I bar will be non-zero.
The first, yes, exactly. Yeah. Mixed control would have all of them. All species would be Y species. That's another way to say it. All species are going to become exchange species.
Would the first 4 terms be constant in time? Right.
If you reach a steady state, yes, because you would have a constant, you would supply and eliminate in such a way that you reach a steady state, yes.
But not the last 4 ever.
Sorry?
The first 4 of the I matrix would be a constant at steady state, but not the...
No, as I said, in that case, here I wanted to take a generic example where I have some internal species, some exchange species. In the CSTR, I would have all of the species that are Y species because all species are exchanged.
Thank you.
Yes.
So in concentration control, the rates of the reaction which are given by K, will not really be dependent on the external reservoir because it's constantly being maintained.
These rates?
Yes.
These rates are fundamental properties of the chemical reactions.
Yeah. So they will, but
it's independent of the supply. This is, think of it like that. This is the probability that an event, a scattering event happens. Given, this is the probability that given that a scattering event happens, the reactions occurs. This is how you need to think of K. It's a purely, if you want to do a theory of that, you need to do quantum reaction kinetics. You need to know the scattering section of the molecules. People spend a lot. You can do it like, yeah, there's a lot of activity in how to calculate this guy, but most of the time in biology, these are simply obtained from experiments. And actually, I will comment on that, how to get them experimentally in a second.
But in the flux controlled system, those
these are, the I's are not properties of the reactions. This is really how you put things into your system.
Yeah.
Okay. Good.
Just a naive question.
Yes.
On your equation, so the only moment when I can see the time is for the flux?
The time is also here. This is the time derivative of the concentration.
Yeah, but so you have the time in this term because there is the time in the flux?
Okay, the concentrations are a function of time. Every concentration is a function of time.
So you will have data with concentration over time?
Yes.
Okay.
Yeah, the purpose of dynamics is to describe how concentration evolve over time. Good. Now, important, steady state. What is the definition of a steady state? I think I will have to adapt my lecture because at this pace. So a steady state is a state where there is no more time dependence in Z. Okay? So what does it mean? It basically means that if you take the general balance equation, that Sj is equal to minus I. Okay? So the rate at which things are exchanged is compensated by the consumption of the reactions. If you supply the consumption, in the sign again depends on the regime. Now, what is a special case of, I should emphasize for notation that in that case, I'm gonna J, and now J is a function of the concentration. I will put SS to say that this is the steady state concentration. Now, a special case of steady state is equilibrium. Equilibrium is much more drastic. You cannot have any flows happening in your system. So basically, J equals to 0. So the flux across every reaction and the flux across exchange with the supply must all be 0. This is a strong constraint. And this can happen in a closed, you can have an equilibrium in a closed system or in an open system. And this will be important. This is not, in an open system, equilibrium is a non-generic thing. You need to control the concentration or the fluxes in, not the fluxes because they need to be 0. So you can not have equilibrium in flux control, but in concentration control, you will have to fix your concentration in a very special way to make sure that these I's are 0. We will get to that.
So in the steady state assumption, you're just assuming that the time derivative is 0, but in the equilibrium condition, each individual reaction has reached equilibrium. That's what you mean. So
Yeah.
the rates cancel out.
It's a very strong condition. But physically, you know that if you have a closed system, your system should always relax to equilibrium. And we're going to use that. This is the key input from physics that we will use. A closed system must always reach equilibrium. Otherwise, you have a perpetuum mobile. Your reactions are doing stuff without you supplying energy, which should not happen.
Can you explain what you mean by equilibrium in an open system again? Because those conditions look almost...
Yeah, it's not trivial. This will really, I will postpone this because it's you need to tune your concentration in concentration control in a very peculiar manner. They need to match certain conditions such that these two conditions are satisfied. And actually, this will depend on the topology. So I will be able to answer only in part 3 if I arrive ever to part 3.
So I have a clarification. So if I understand equilibrium and steady state in a way with this equation written, mass action law, so is equilibrium like both the forward rate and the backward rate is 0? And that's why forward minus backward is equal to 0.
Exactly.
But steady state is they are non-zeros, but they are the same. So the forward rate is equal to the backward rate, and hence
constant. Yeah.
The constant, they're non-zero, they're constant, and the value is the same, and hence the flux is 0. Can I understand it like that?
The last part. So this will be constant, this will be constant, but their difference is going to be non-zero.
Okay.
At steady state. At equilibrium, this will have to be equal to this for this to be equal to 0.
0. Okay. So then what is the dz by dt equal to 0? That is not same as this, right?
No, look, if I put, this is my condition. I'm saying my species do not evolve anymore in time. They stop depending on time. So let's go here. This is my balance equation. This is telling me that this must be 0. So this must be equal to this.
Right. Okay.
2 minus this.
Okay. Got it.
I have one more confusion about the open system equilibrium. So if I set I to 0, doesn't that essentially close my system?
Yeah. Which is why I said in a closed system, I don't even need to specify this. It is satisfied by, let me do it like that. In a closed CRN, this would be the condition. In an open CRN, this would be the condition.
Right. So it means that in equilibrium, I cannot have exchange with the outside world. Yeah.
Every flux, every net flux, net, this was an important comment because net means the difference. You will always have processes going in 2 directions, but they cancel each other. Okay, thermodynamics. How much time do I have left? Half an hour, okay. Okay, I may start skipping certain derivation because otherwise I will not make it. Alternatively, I should move to slides on the second presentation. You'll tell me. Okay, as I said, we will now, since at the end, I want to use the fact that a closed system always relaxes to equilibrium, must relax to equilibrium. We will revisit the equilibrium of a mixture, an ideal mixture. Zoom that collapsed or? No, it seems to be working. You can. Okay, so now let's even imagine that we shut off the reactions. We are simply talking of a mixture at equilibrium. What is the no, I wanted to say more before going to that. So equilibrium before equilibrium of closed CRN. So as I said, G of Z equilibrium, all the fluxes must be 0. At this equilibrium, I will put Ek when it's an equilibrium concentration. And this means in the closed CRN, we don't have I, that for every reaction, K rho plus rho times the concentration of the reactant must be equal. I'm basically, this is the condition of R rho equals minus R minus rho. Okay. From that, I can deduce that the ratio of K rho divided by K minus rho is, you remember the stoichiometric matrix is the difference between minus rho and rho. So this is going to be equal to the concentration at equilibrium to the power of the stoichiometric matrix. And this is rho. So this is the matrix, but I specify rho, so it becomes the vector. Vector in species, because I specified the reaction. So if I specify a reaction, it's like specifying a column. And still with this notation, you remember, the notation is this product. And this is what is sometimes defined as the equilibrium constant of the reaction. The equilibrium constant, yes, of the reaction. And you see that this is interesting because it provides you, it's highly non-trivial, it provides you a condition between these rates that have to do with the chemical kinetics, the ratio of the rates, not the only, it's only the ratio, not, it doesn't fully specify the case, but the ratio is related to the concentration at equilibrium. Okay, yes?
Just a question. So sometimes you have the flux in a matrix, sometimes it's just the flux. How do you choose your notation? Because like for this thermodynamics,
okay, let me then put a row here. So this is the flux in a reaction that needs to be 0. So the rate, this is R rho. This is equal to R minus rho. So this is a number. Okay? And now, because I will use it later, I define RT log of this K rho over K minus rho. Since this is a product by the definition of this notation, I can rewrite this as RT log of the concentration. And now I again introduce a bit of fancy notation, but it's important. The log of a vector, you should read it as component-wise log of each Z alpha. Okay, so this is log of Z. Okay, and since it's a product, I can log of the product becomes a sum. And so now I have this vector times this vector. Which is
so just to confirm, the S rho is technically the column vector of the reaction, right?
Yes.
Like for column vector of the S stoichiometric matrix. The row will be the column vector because that's the representation of the reaction.
Exactly. One row picks one column. So check a bit of the algebra, because if we stop on every step of the algebra, we'll never make it. So I will try to go on. I'm okay with questions, but let's not go too much into the details of that. Otherwise, we will not make it till the end. Okay, now I go back. I go to what I wanted to say. I should not cross that line. I will maybe erase. Well, let me start here. Good. So I go now to my ideal mixture. So this is, conceptually, it is important. Maybe I will skip the derivation, but I want to give the idea because it's important to understand why we will choose as equilibrium potential what we will use. So as I said, we are dealing with solutions. So we have a solvent, which is typically water, okay, for us. And we have the vector of the species. So water is always at equilibrium. We assume it doesn't change. And in the theory, I could also go in how to derive this from equilibrium thermodynamics, but this is really textbook. So that part I will assume that we can accept. This is the sum of the chemical potential of each, that depends on the concentrations, times the concentrations. I will actually skip this dependency because otherwise it becomes heavy notation. So mu depends on the concentration times the concentrations plus mu 0 times the concentration of 0. So you should think of mu as the energy associated to each molecule. So again, because we are in dilute solution, this is much bigger than this. And the chemical potential, its form, is the standard chemical potential that is a reference. I recommend for you to think of it, that's how I like to have it in mind, and it can be justified. This is really the intrinsic property of the molecule. It's the amount of free energy contained inside one molecule. You know, a molecule has bonds, has a structure, and also an entropy at equilibrium. Not only an energy, but also an entropy, because at finite temperature, it can change configuration. So the molecule at equilibrium in solution has that free energy. And then there's the contribution from the fact that we have many molecules in the solution. And this is the log of the molar fraction, which in this case is Z alpha over Z alpha plus Z0. And if I now take the mu 0, it's going to be the standard potential of water. Yeah, standard has sometimes the bar like this. Yes, RT log Z0 over Z alpha plus Z0. Is this clear? I'm simply taking the energy of the molecule multiplies by the abundance. It's pretty straightforward. But what is important is that the solvent is here. That's why I wanted to do this calculation. Now, I will skip the derivation I was planning to do initially. But it's very straightforward. You can try it at home or in your room. I will use this. You had a question? Sorry, what? I didn't hear.
Yeah, the G, what exactly does it?
This is the free energy. The Gibbs free energy. Because the right potential in thermodynamics, when you are at temperature and pressure fixed, is the Gibbs free energy, which is the enthalpy minus T times S.
So Z naught is the concentration of the solvent.
Z naught is the concentration of the solvent.
Thank you.
Okay? And now I state that if you do its Taylor expansion, you use this in these two expressions, okay? You can basically get to the following expression. Let me then now move to the next. Maybe I will cancel. Cancel this. Okay, so after doing this expansion, what one gets is that the G of these Zx can be rewritten as the sum over alpha, mu alpha of the concentration at equilibrium. And I will redefine alpha now, the mu alpha. And this is the term that is, I wanted to do this calculation to explain where that term comes from. Is RT, it comes from that expansion. So it's if you want, you can see it as a solvent effect. Plus mu 0, 0, Z 0. And this is to be written as plus order 1 over Z0. Okay? So I assume that the solvent is in large abundance. So what about this guy? This guy now is mu alpha 0, which has been redefined. I should say that. I should have used, okay, yeah, I skipped those details. Yeah, I rewrite it. RT log concentration of Z alpha. Okay, so now I kind of got rid of the solvent, if you want, explicitly, because this is a constant. We can neglect it. In every change, it's not going to play any role. It's like a baseline for energy. And now we express everything only in terms of the concentrations of the species that we care about. But you see there is this RT here. And it comes from that expansion. Okay, now that we have that, let's do the following. We know that in thermodynamics, equilibrium is a minima. So this means that any small perturbation around equilibrium should have its derivative 0, because it's a minima of the free energy. What are the perturbations here? We started from an equilibrium solution. It's the reactions, right? The reactions, they convert stuff, so they can slightly change concentrations. And so we will look at what happens when a reaction changes a concentration, and knowing that it needs to be a minimum. So condition of minima, first it's important, this you can also check. It's a simple calculation. The derivative of G divided by Z alpha is actually giving you exactly mu alpha. And this is also consistent with thermodynamics. We know that the definition of the chemical potential is the derivative of, and these are all equilibrium. No? So this, if you take the derivative of G, you get mu. And now think of it as the condition of a minima. The reaction implements a little change. And because it is a minima, that change must be 0. So the delta G caused by the change of G due to a reaction, this is a function of the equilibrium concentration, will be equal to the chemical potential, which is this derivative, times the stoichiometric matrix, which tells me the increment by which, so I specified rho here, the increment by which it's sometimes called the degree of advancement of a reaction. So there's been an increment of Z due to S, and that increment must be such that G is minima. So, you know, this is like perturbation times derivative. It's like the first order perturbation. This needs to be equal to 0. Okay, that comes from the requirement that G is minimum at equilibrium. And now the reactions implement little changes, but I'm at the minimum, so the first derivative times the change must be 0. Good. So notation-wise, yes. So this is the delta G of a given reaction. I can think of this as also as a vector if I, in terms of, but this is why I only chose a column. Okay? Now from that condition, remembering the definition of mu here, I can basically get that delta G0 now, and delta G0, I define it to be, I put a minus because of what I'm going to do next. The standard chemical potential, this depends on T and P times this quantity, because you see, mu has this part and this part. So now I'm using this into this, and I'm identifying this part will be equal to the other part. And the other part is RT log concentration of Z ec times S rho. And this, we had it here. You see? I forgot to put the ec. It's here. So this is equal to, let me write it here. RT log K rho over K minus rho. And this was also our T log equilibrium constant. Now this is what, this is important. This is, in modern language, what we would call local detail balance. What Simone would call generalized. But traditionally has been referred to, why haven't I written this here? Ah, no, this comes later. Okay. Yeah, no, actually, this is not really what we decide. We call, no, it's the one non-equilibrium with the delta G. Okay, sorry. Let me not call this the local detail balance. But this is a very important relation. You see, we use the fact that we are at equilibrium, that the solution is at equilibrium, huh? And what we get is that the change of mu0, you remember there were these discussions last week, what is the difference between the delta G and the delta G0? Now, we will see later what is the delta G. But now we understand what is delta G0. Delta G0 only contains these intrinsic energies of the molecule, how they change through a reaction. So this is really the change of the internal energy of the molecules before and after the reaction. And we can express this in terms of the equilibrium concentrations. Okay, because as we saw there, the ratio of these equilibrium concentrations is related to this ratio of kinetic constant, and we can also relate it to the equilibrium constant. So what this means is that the delta G gives you an idea of at equilibrium, only at equilibrium, whether you will have more products or more reactants. Okay, if the delta G is the delta G0 of a reaction is positive, then the K will be displaced towards the reactants, right? Because K, yeah.
I think just there are two comments. One is a small thing of a formalism. Maybe the equilibrium constant, that's for reaction rho, right?
Yes, thank you.
That's a small notation thing. The other thing, just for clarity for the students, maybe it would be useful to summarize the difference between that relation with the G, with calculated for the equilibrium concentration, and the variation of G0, because I think there's a subtle difference, which
I know, but that is really, it's because I use this, right? I split this mu here contains the mu0 part and the log Z part.
Yeah.
So here I have the full mu. And I know that at equilibrium, this must be 0 because it's the minima of G.
Okay.
And from that condition, by splitting the two contributions here and here, this is only a definition. So this is one piece is equal to the other piece. So this is really the part coming from mu0 is here.
So G0 is the sum of the mu zeros.
G0, this is the change of mu zeros due to a reaction.
And then in the next step, you use the.
Okay, let me do it explicitly. If this guy is mu0 plus RT log Z, what I do is I put RT log Z on the other side.
Okay. So then that's, since that's 0, okay.
You see? Good. And this is what provides me this connection between the mu zeros, which are intrinsic property, and the kinetic constant and the equilibrium. So this is all equilibrium now. Huh? We haven't got out of equilibrium yet. Yes. How much time do I have left to go out of equilibrium? 1 minute.
It is appropriate
to go out of equilibrium. Okay. Yes. I will have to adapt a bit the speed. Okay. Let me then conclude here. So now you remember this notion of GX. Maybe let me just this so that I can use it as the starting point for next time. This we took it as the free energy of an equilibrium mixture. We turned on reactions. We said it's an equilibrium, so that should be a minimum with reactions. We got this condition. But now the claim will be, I will take this form here, and I will say I can still use it out of equilibrium when the concentrations are not equilibrium concentrations anymore. This is sometimes called local equilibrium assumption. What it means physically is that what drives the system out of equilibrium are the reactions, because they change the abundances. But whenever the reaction happens, very quickly, the species will equilibrate. Okay? And so it's like reactions is the thing driving the system out of equilibrium, and also exchange, because this changes abundances. But right after a reaction event, the molecules very quickly goes back to equilibrium. And if I would turn off the reactions again, I would be at equilibrium. So this is why we're going to use this form of G, but with non-equilibrium concentration as the starting point for the next slide. And we will see of how it evolves and how we can split it in terms of different contributions. Okay.
Yes, I just had one question about that equation.
Yes.
At least the first term is not making dimensional sense to me because there's already two concentration terms that are being multiplicative there. See, mu alpha, Z alpha at equilibrium, and then there is also a Z equilibrium concentration being multiplied outside that bracket also, which is not making dimensional sense.
Yes, that's a very good point. That's because I forgot the parenthesis.
Right.
This is simply the dependence of the mu in terms of Z. Sorry about that. Good point.
I had a question. So you say that the chemical potential is the standard chemical potential plus RT times the mole fraction. So shouldn't that also include the fractions of the other species? So you've only included the alpha species you're considering and the solvent. Shouldn't it also include all the other species in the reaction?
This is precisely why I'm saying it's an ideal solution. You see, if there would be interaction, you're right, the chemical potential of alpha would depend on all the species it interacts with. And we can generalize to that, but then it's simply heavier.
So that is in some way your definition of an ideal solution, that the chemical potential doesn't depend on only on the solvent and the alpha species.
Yeah.
Okay. And I mean, so rho indices the reactions and alpha indices the species.
Yes.
Okay.
Yeah, I should have emphasized.
If there are no other questions, it's time for lunch. So let's thank Massimiliano again for the very nice lecture.